Okay, today we're going to answer the question, what the heck is Word2Vec? Now, if you don't have any idea whatsoever Word2Vec is, Word2Vec is a method basically for turning words into numbers. Now, why is that important? Well, because once we turn words into numbers, we can compute on them and we can do interesting, cool computery things. We'll talk more about what exactly that means down below. But first, let's just preview how we're going to spend our time together. I'm going to walk you through building up to the explanation of Word2Vec in three parts. So first, we're just going to go ahead and say, why all the fuss, and help motivate why does you want to continue watching the video. Then we're going to do a really quick overview of machine learning. We'll quickly talk about linear regressions, logistic regressions, and then introduce the idea of neural nets. We're going to do that all. We're going to talk about some math, but we're not going to ask you to do any math. It's going to be a very high-level introduction. Hopefully that you'll be able to walk away with some understanding of what's going on in these different machine learning tools. And then we'll end with an explanation of Word2Vec, which by the time we get there will hopefully make sense. So what's motivating this? Why all the fuss? You may know about some AI tools in law, right? So a lot of people say, oh, our system uses AI this, AI that. But what are some concrete examples? Well, one, there's an issue spotter that we're building here in the Lit Lab to find legal issues and lay people's questions. And we're doing that. The first part we did in partnership with Stanford's Legal Design Lab, where we actually had, and we are continuing doing it. You can continue to play this game if you like. We've set up an online game that allows people to lay people's legal questions. And so that's sort of a crowdsourced thing, creating training data that we'll be using to train a machine learning issue spotter. And so that's an example of some AI in the law thing. Another thing you might have run across is this tool from Casetext called parallel search, which basically allows you to search for a legal proposition. It's like searching through case law, but instead of having to have exact keyword search or do all sorts of fancy stuff, you just type out the sort of proposition of law that you're interested in, and it matches that against its collection of legal opinions. But it's not matching against the exact words you put, it's matching against the sort of semantic meaning of the sentence you said. So you don't have to use the same words that the opinion used, you just have to use words that mean the same thing, roughly speaking. And so you might be asking, well, wait a second, how do we train a computer to be able to do anything with language? How does it know the meaning of a word? Or words. And we've talked some before in previous levels about how if you can turn words into numbers, you can do all sorts of interesting things with them. But obviously the important thing is you have to have a good way of turning the words into numbers, a way that somehow captures the meaning of the words. If you just took words and randomly turned them into numbers, there's no information content there, and you want to be able to do all the cool things that we do. So the question is, if we're going to do all these cool things, how do we do that? And that's really the question behind Word2Vec, because Word2Vec is super cool. How cool? Well, let me just explain to you a little bit about how cool Word2Vec is. It's actually kind of like magic. So Word2Vec will take words and turn them into numbers. Now, what I mean by that is there is a unique set of numbers for every word that Word2Vec is trained on. So if you think about it like if it's been trained on every word in the English language, there's a unique set of numbers for every word in the English language. And that unique set of numbers can be thought of as some sort of semantic space, right? So think about it this way. There's, for every word, there's 300 different numbers that are associated with that word. And those 300 different numbers, you can think about them as numbers on a number line. And so you can think about, X and, sort of X and Y and the Z axis. And then just imagine adding like 200 and some odd more, or 1,000 more dimensions and 1,000 more numbers. So in 3 dimensions, you have 3 numbers associated with something. If you have 300 numbers associated with something, you can talk about that as 300 dimensions. Anyhow, don't try to wrap your head around it too hard. The point is you can plot a point basically for each word in this semantic space. So this space has 300 different dimensions, and for every word, there is a point in that space where that word is represented. So here you see a sort of a 3D projection of some words from that 300 dimensional space. That just help us visualize it. And the thing that's really cool about Word2Vec is that, say you have the word king, okay? And you subtract from it the word, so that word king has some 300 numbers associated with it. It has a spot in that semantic space. If you take that spot there, so let's say here, and you take the word for the representation for the word man, and you subtract out the word man from the word king, and then you add in the number for the word for the word woman, then it turns out that you end up in a spot in that semantic space that's really close to the word queen. Well, now that is pretty amazing. You can start to do math on words. And it's not just being able to subtract man and add woman. You can do things like look at the tense of words. You can move from a country to a capital, because in this very large semantic space, there are different directions that correspond to different things. And sort of one is sort of, you know, the tense might be the tenses of verbs. And so this is really, really exciting stuff. We've talked before about this a little, and we mentioned that there can be issues, right? Because if you take doctor minus man plus woman, you don't actually end up next to doctor again. You unfortunately end up next to nurse a lot of the times. And that's based upon the bias of the data that these models are trained on. But that's actually really a powerful statement about the fact that these models are able to capture information inherent in the data they were trained on. So they're capturing the biases that exist in that historic training data. The point is that the tool itself is somehow producing this numeric representation that captures all that, this sort of meaning in the words. It's not all the meaning in the words, it's that it captures some meaning in the words, sort of actually sort of like a sad shadow of the meaning. But the fact that you can do these mathematical manipulations on words should impress you with the fact that it's doing something really, really interesting. And then, of course, there are all sorts of, if you have a numerical representation of words that has some meaning in it, then there are all sorts of interesting things you can do, such as those examples that we just talked about, like parallel search and being able to do issue spotting using machine learning. And so that's why that's why Word2Vec is cool, because somehow it takes words, it turns them into numbers, and those numbers have these properties such that it still maintains some of the semantic meaning or represents some of the semantic meaning of the words in that numerical representation. So let's go ahead and talk really quickly about machine learning. Right, so we've talked about it a lot in previous levels, but if you sort of boil it down to it, machine learning models are just going to take in a number, and based upon that number it takes in, it's going to spit out another number. Right, so this is sort of the black box that we've talked about before. We have some number X, it goes into the black box, and then out comes some number Y. So really, this probably looks familiar to you. This is just a mathematical function, right? And so we've dealt with different functions as we've gone through the course. So the first one that we know is a linear regression, right? And that's your good old y equals mx plus b, right? So it's the equation of a line. So let's just really quickly remind ourselves of how that works. If I have here a scatter plot, so I have a bunch of dots, what I do is I can change the equation of the line. I can change the coefficients here in the equation of the line. Here I'm changing the slope, and here I can change the intercept. And basically what I'm doing, if I'm doing a regression, a linear regression, is I'm trying to get a best fit line. So a line that goes through that scatter plot in such a way that I minimize the error where the error is defined as sort of this relationship between the line and where the dots are. And we've talked about R squared and all that sort of stuff. But the point is that what you're doing is you have these sort of dials. You can sort of think of like these little sliders that you're changing, and you change them until your error is as small as it could be. And how exactly you do that is not important. The point is that you're just sort of changing some of these parameters about the equation of the line, and you're getting a best fit line. All right, so that's a linear regression, and that's a great thing. You can take historic data of something, and you can put it in, and you can get out a line which you can use to help predict future data. So you can say if data came in, we go back actually to our example here. I can say if I get an x of 6, then my model is going to suggest that it's going to be very close to 6 as the value outwards, assuming this is the right best fit line, right? It might not be, so it might be a little different if we were actually to calculate it. So that's the power of a linear regression. Well, what about some other things we've seen? Well, we've also, I'm going to take a quick footnote though, actually, a quick detour to mention sort of a quick footnote. Fun fact, all of those scatter plots have the same summary statistics. So the mean and the x and the y coordinates is the same. And the best fit line through all of those is the same. And that's just, I couldn't be talking about, playing around with our graph there for linear regression and not just mention this fun little footnote. So this is just because I didn't have another place where we were going to talk about it. And this is just to tell you that you should, whenever possible, look at your data because what's really going on might be different than you might just guess from the summary statistics. And sort of a fun thing, and this is called Anscombe's quartet here, which is these 4 graphs that sort of illustrate this point. But I think the point was actually illustrated really, really well just a couple of years ago by some folks at Autodesk. They created something called the data source Doesn. And so actually there are 12 different scatter plots that all share these same summary statistics. And of course, one of them looks like Tyrannosaurus here. And actually we can just sort of see here are all the dozen different ones, and they actually just made these plots based upon doing little perturbations to the points on the plot to get them to go where they wanted to without getting out of the bounds of these summary statistics. So you can see there that if you look, the first 2 digits are always the same for these summary statistics, but out beyond that, there's a little motion. All right, that being said, back to our models. So we've talked about linear regression. We've also talked about logistic regression. Right? So logistic regression, and we'll pop back over to our browser here. Let me switch over. I have a logistic regression here, or a logistic function. Logistic regression makes use of a sigmoid, which is this equation here. And so in the same way that you had a scatter plot and you were trying to fit your line to your data, in a logistic regression, you're trying to fit this sigmoid to your data. And so usually what you end up doing is you have your data coming in and it has a value of 0 or 1 is what you're looking for. So either this is motivated by our is school closed example we've talked about before. So if you were trying to model, say, whether or not an event was going to happen, you could say either 1 means it did or 0 means it didn't. And so we can think about this x-axis here as the accumulation of snow on certain days, and 1 means that school was closed, 0 means school wasn't closed. And so we can see when the accumulation's not very big, school is closed. And then when it gets bigger, so not very big, school is open. And when the accumulation gets up beyond 6 inches or 7 inches, then school is closed. And so our job when making a logistic regression is to find a way to fit the sigmoid to that data. And so again, just like our linear regression, there's an equation, and basically we change some of the variables in the equation such that it then will fit our data. And so now this equation, this sigmoid, could be used to predict the chances that school was going to be open or closed. So if I look and I see, let's say there was 5 inches of precipitation of snow, and then we see there's something, there's like a 70% chance that school is going to be closed. Okay, and so that's our introduction of logistic regression, or revisiting logistic regression. So now we've got linear regression, we've got logistic regression, and it's important to realize that we can take in multiple inputs, right? We're not bound by just having X, some function, and then Y. We can take in multiple inputs, right? So we saw this in the big bias and big data. This is an image from that, where we were looking at both the mean income of a defendant and the seriousness of the charge. And so we were able to take those, and all we did was we just added another dimension to our calculations. So instead of doing a best fit line, we did a best fit plane, right? So you can take in more than just one. In fact, you can take an arbitrary amount of inputs when we're creating these functions. And it's not just linear regression. You can do that with logistic regression as well. And so now the question comes up, well, what next? Well, first, it's important to realize, like I said, you can have an arbitrary amount of inputs. So not just two, not just one, you can have hundreds. But let's move. I want more. Well, so right, you can take you can have two logistic regressions right next to each other. They both will, each is a copy of the same thing. Great. They're both saying the same thing. If you trained them to do the fitting, they'd be exactly the same. But what happens if I do a nifty thing here? So I have these two logistic regressions that are identical to each other right now, and I add in a third. Well, what you're seeing here now is what people think about or what people mean when they're talking about a neural net. Now you'll see that I actually put a little tilde in front of logistic regression there because it's not quite a logistic regression anymore in these little boxes. It's the same idea. You have inputs coming in, which are some numerical input, and then it's spitting out a numerical input between 0 and 1. Actually, in modern neural nets, that's not always the case. Sometimes they go between -1 and 1. But originally, neural nets actually used the sigmoid function, which is the same function that you're seeing in a logistic regression. So the point is, inputs come in, and then in each of these boxes, we call these boxes neurons, they then spit out a value between 0 and 1. And so what's happening is it goes in to say this first neuron here, all the inputs come in, it's going to spit out some number. Again, all the values going into this neuron here, it's going to spit out some number. And then this guy's going to take in those two inputs and then spit out some number. Now, the reason why it's not quite a logistic regression anymore is, remember, the logistic regression was fitting that sigmoid to our data. Okay. Here, it's not quite clear how that would happen. If I was looking at, say, accumulation, precipitation for accumulation, wind speed, and say maximum temperature, I could see how that would go into logistic regression and maybe spit out a value of the odds that school would be closed. But what's the value here mean? Or how would I even train that if my closed or not closed value is here in this part here? We have to figure out some way actually to figure out how to move those sliders in each of these functions. And so it turns out there's some fancy math that people do to do that. It involves some calculus and something called gradient descent. You don't need to concern yourselves with those details right now. The point is that a neural net is, if you squint, it's really just a collection of logistic regressions. Not quite, but like I said, if you squint. So numbers come in, they go through something like a sigmoid, and then it spouts out a number between 0 and 1. And then that feeds on to the next one, which then takes some of these inputs and then does the same thing all the way down. And what happens is that the process of training a neural net, instead of doing this best fit line thing like you do in a linear regression where you're moving a line until you minimize the error that is created by where the line is, or in adjusting the sigmoid until you minimize the error that is created. What you do is you fiddle with all the dials and knobs in all of these different neurons until you minimize the error that is created between your predictions and reality. And so that's all a neural net is. And it's you have some inputs, you have this end output, and then you can train it in the same way that you might, in an analogous way, to say a linear or logistic regression, which is to say you're trying to minimize the error of your output. And so that's what we saw when we moved our equation to the line or moved the sigmoid. We're trying to minimize, effectively sort of minimizing the distance between the, or approximately sort of minimizing the distance between the equation you have and your data points. So here, again, you're trying to minimize the difference between what you're putting out here and what the actual answer is. So if you were saying yes or no, you're trying to get the most highest fidelity model that's going to do the best job of replacing, replicating that saying yes or no. So that's a neural net. So that being said, then the question comes up, well, what the heck is Word2Vec? Okay, so here is an example of Word2Vec, really oversimplified. In Word2Vec, basically, you can build Word2Vec based upon a neural net. So in this first column here, what you do is you actually have a input for every word, right? So of course you have to train these things on some corpus of data. So maybe it's all of Wikipedia or all of the web or something like that. So it's going to be every word that's in your corpus. And basically the value is going to be either 0 or 1. It's going to be 0 if it's not the word that you want to deal with, and 1 if it is. So you have all these inputs, one for each word. And if I'm interested in the word be, I'm going to make that one have have that input have a 1, and everything else will be 0. And then I'm doing the same neural net architecture. That 1 gets passed to this neuron. It gets passed to this neuron. And oops, I didn't draw it in my line. My line's missing. And it gets passed to this neuron. But it's basically taking in these inputs, and then it's spitting out a number. So here's, this one's going to spit out 0.1, this one's going to spit out 0.5, it's going to spit out 0.2. Why does it do those numbers? Well, it does those numbers because that's where the dials, where it played around moving all of the sliders to the point where then these numbers were sufficient to get the results we wanted here. So again, we see our words again, but what now this column is this is the probability that this word will occur close to the input word. So the point is, if I go ahead and I've trained this right, and I imagine my corpus is probably bigger than this, but if my corpus isn't, B is probably going to be close to all and back, right? Or it's more likely that it's close to all and back than it would be close to let it or go, okay? And so, and you can imagine it for a different word, for say it, you know what, that should really be 1 there. And of course, this becomes a 0. So for a different word, for it, we can see that there the probabilities change, which is to say that it is probably next to let and go, more so than it's next to all or be or back. Now, those probabilities come from your corpus of data. So it comes from whatever text you were training this on. So what you're doing is you're feeding in a bunch of data such that when it's there, you want the probabilities that are the sort of numbers that are coming out of this guy here to reflect the probability that that word is going to show up near this word, okay? So you have what's called a one-hot encoding, which is to say that it's just a 1 for the word that you want. That goes in to this neuron, and this neuron then passes something on to another neuron that takes an input from this layer of neurons and then spits out a probability. Now, if you've heard about deep learning is just a neural net where there are a lot of what's called these things are called hidden layers. These layers are between your input and your output, so you can have multiple layers. And if you have a deep set of layers in your architecture, then that is associated with something called deep learning. But what's really interesting here is we've trained a model such that it basically can predict whether or not a word will be near another word, just based upon the statistical occurrence of that word in this corpus of sentences, right? So what we basically did is we would read through, say, all the lines of Wikipedia, and we'd look at the words, sort of on either side of our sort of target word, and say, well, what's the likelihood that this word is going to show up next to this one? And that's effectively what we're getting here. And so what's interesting is that we've trained this model, but what we're going to do for Word2Vec, what Word2Vec does, is it basically just takes these numbers. So you'll note that there would be different numbers for different words because they have to be different to produce these different probabilities here. And what's really interesting about the properties of those numbers is we've taken this might be this here might be a column with 30,000 or 100,000 rows, right? Because there's a lot of unique words in your text. This hidden layer is often usually kept to something like 300. So that means that if it's going to then represent back out, and then this, of course, this column here is again back out to our 30,000 or 100,000 rows because it has all the words in it. If we're somehow going to get it such that a consequence of the fact that we've trained this model in this way means that words that have similar meanings, right? And it's correct to say that words that have similar meanings will happen to co-occur with the same type of words. And the consequence of that is that when fiddling with all the dials to get these numeric representations, a consequence is that words with similar meanings are going to have similar numbers, which is to say that in this sort of weird, big global space, that words with similar meanings are going to be close to each other in that space. And it's a consequence of this fact and sort of this compression of all of the words down into these 300 rows here that give Word2Vec the abilities that we saw before, which is to say that these, in this case, there are 3, but normally it's something like 300, those 300 dimensions associated with the word are what are going to give us all of that amazing magical behavior that we talked about, where we can do math on words. That being said, hopefully that sort of helps give you some idea of what the heck Word2Vec is, which is that it is a means for taking words, turning them into numbers, such that those numbers have these interesting properties that they maintain some of the semantic information of the words. And the way you get those numbers is by creating a neural net, training it to spot, to determine how likely it is certain words are to be close to one another. And then basically taking these what's called the weights on this hidden layer, which is to say sort of these numbers that tell us how important this feature is to determining things, and taking those and using them as the numeric representations of your words. And so every word is going to have a different set of those numbers, and that different set corresponds to a space, a place, a location in this giant semantic space. So hopefully that gives you some idea what's going on. If you want to sort of get your hands dirty, sort of get a better feel for what's going on, I'm going to share with you a little treat. So I'm going to go back to the browser here, and we're going to go over, we're going to look at this visual inspector. So back to my browser, and then I have to open here. And so what this does is this is an implementation of a neural net. Here, instead of, it's just looking between two words co-occurring with each other. So eat is with apple, eats also with orange, eats with rice. So what it's looking for is a sort of a very artificial way of putting these things together. So instead of having to train on 30,000 words, here we're just training on, these couple hundred characters. And what it's going to do is it builds up a neural net. Red means like yes, yes, yes. And blue means no, no, no. And so what you can do is you can see that at first, this neural net is just randomly assigned weights. So if I look at this here, there's like, it's not really lighting up. But what I can do is I can train this over many generations. And you can learn more about exactly what's going on here by reading this, everything you need to know about this tool. There's also a link below with a video from the author of this tool. And after a while, it's been trained such that now I can see that Apple has these different weights, okay, which is to say that like here, the reds are, remember, sort of really close to 1. And we can see that this lights up juice. So apple and juice somehow are related to each other. And what's interesting there, right, is that, so this third and fourth node was really, really red. So let's see if we can find any other things that light up juice. I'm gonna check that. That sort of gives me a little juice. Drink sort of associated with juice. Eats lights up apple, orange, and rice. That sort of makes sense. Juice on this side is associated with drink. Milk is associated with drink. Orange is also associated with juice. So now here's the important thing, right? So orange is associated with juice, and you can see that it also lights up 3 and 4 rather strongly. And what that means is if these were, again, this is where we got the numbers for our Word2Vec, that this is, very close to 1, this is very close to 1, in the same way that Apple here has it, so that this is very close to 1, this is very close to 1. You can see actually those, the way Apple sets things up is very similar to orange in its sort of color distribution, which is to say in the numbers. So right now here we have like a 5-dimensional space for our Word2Vec. And you actually sort of, you can sort of visualize that here too. This is a fun little thing to play around with. You can do fun stuff with, come up with like other pairings. Here they have the famous king and queen example. I'm trying to do something with that. And then you can see here sort of a projection of those things. But this is just sort of a fun tool. There'll be a link below. You can play with it. But hopefully you now can answer the question, what the heck is Word2Vec? It's a creation of numbers for words using a neural net to create those numbers. And through a really sort of clever way that maintains a lot of really interesting properties. And really is encoding some information about the meaning of words, just based upon the fact that similar words are going to be next to the same other words in different contexts. And so there you go. Now you know what the heck is Word2Vec.